This section covers the organization of code as programs grow in complexity. While small programs may function perfectly well within a single file, larger projects require a much more structured approach to manage numerous classes and functions. That is where modules come in. A module is defined simply as a Python file. For instance, if a project contains two Python files, it effectively contains two modules. This modular structure allows a class defined in one file to be loaded and utilized in another. Let's consider the development of an e-commerce system. Such a system requires extensive database interaction. To maintain organization, classes and functions related to database access are placed into a separate file named database.py. Here we might define our core database class. Other parts of the system, such as a module named products.py, which handles product queries, must import that database class to instantiate it and execute queries on the product tables. This is achieved using the import statement, which is the primary mechanism used to bring modules, classes, or functions into your current workspace. A very common example is utilizing Python's built-in math module so that we can access the square root function for distance calculations. There are several import syntax variations you can use. One approach involves importing the entire module. When you do this, the module is added to your namespace, which is the list of names currently accessible within your working file. Alternatively, a specific class can be imported. This puts just the database class directly into our namespace. If a naming conflict occurs, you can rename the imported class using the as keyword. By writing from database import database as DB, it shows up as DB locally, preventing any confusion with existing classes. Furthermore, you can import multiple items in a single statement, bringing both the database and query classes into your namespace at once. While some sources might suggest importing all classes from a module using the star syntax, there are severe dangers to these universal imports in professional development. First, it clutters your local namespace. If you import everything, it becomes incredibly unclear where a specific function or class originated. Using an explicit import statement ensures that even hundreds of lines later, you know exactly where a component came from. Additionally, universal imports frequently break modern IDE features. Your editor loses track of the source, resulting in no code completion and the inability to jump to a definition. Finally, this syntax leads to unexpected behavior through transitive imports. If module A imports from module B, a star import might accidentally bring in objects that were themselves imported into B, severely polluting your local namespace. The key takeaway is to always use explicit imports to keep your codebase clean, traceable, and predictable. As your project expands beyond single files, we will next explore how to group these modules into nested hierarchies called packages.
As our projects grow, we need better ways to organize our code. While a single file is fine for a small script, a large application needs a structured approach. Let's look at how we manage packages and hierarchy. Since modules are just single Python files, Python uses packages to provide a further level of abstraction. A package is simply a collection of modules stored within a folder. But how does Python know a regular folder is actually a package? It requires a special file. This file here, named init.py, is usually empty, but its presence is absolutely mandatory for Python to let you import modules from that folder. Let's trace this out on our e-commerce project directory. We start with a parent directory containing our main.py file. Inside that, we have an e-commerce package folder, which contains its own modules and its mandatory init file. As we get more complex, we can even have a nested payments package inside the e-commerce folder just to handle things like PayPal or credit cards. This nested hierarchy allows for logical grouping, keeping our core logic separate from specific implementations. Now, how do we actually bring this code into our files? Python supports two primary methods, absolute and relative imports. Let's look at absolute imports first. These specify the complete, full path to the module or function from your project root. For example, to access a product class, you would write import ecommerce.products or from ecommerce.products import product. Notice how the period acts as a separator between packages and modules? These work from anywhere in your project, as long as the packages are in your Python path. On the other hand, we have relative imports. We use these when working within related modules in the same package. Instead of typing out the full path every time, we use a period to represent the current location. For instance, a single period like this tells Python to look for the database module right next to the current file. If we need to navigate further up the tree tray, we use multiple periods. 2 periods represent the parent directory. You can even combine this, like in the third example, moving up to a parent and then down into a different package called contact. Moving on, let's discuss module state and delayed initialization. Modules can store global state. Instead of creating a new database connection in every single file, we can create a single database object right at the module level in database.py. This object is created immediately when the module is imported and then shared across the application. However, this immediate execution can cause a really slow startup time if the initialization is resource heavy, like connecting to a remote server. To prevent this, we use delayed initialization. We wrap the creation in a function like initializeDatabase. Inside this function, we must use the global database keyword. If we don't use global, Python just creates a temporary local variable that disappears when the function ends. By delaying it, the connection only happens exactly when we actually need it. This brings us to an important rule. All code at the top level of a module executes immediately upon import. To prevent a script from running accidentally, when you just wanted to import a class from it, we use script execution control. Python provides a special variable called name. If you run a file directly from the terminal, Python sets this variable to the string main. But if the file is being imported, it sets it to the module's name instead. By wrapping our startup code in this if statement block, we guarantee it only runs when we execute the file as a standalone script. Finally, let's look at inner classes. While we usually define classes at the module level, Python lets you put them anywhere, even inside a function. Here, the default formatter class is defined entirely inside the format string function. Because it's scoped to this function, nothing outside the function can ever access it. It's a great technique for one-off uses that only makes sense during that specific operation. So to tie it all together, methods reside in classes are organized into modules, and modules can be grouped together into